Thank you so much. That was one of the best introduction I've ever had for my research talk. So I'm really humbly honored to be having such introduction, Professor Shin. And as Professor Shin mentioned, we first met when I did a visiting research at Cranfield University before Professor Shin joined KAIST. And one of the research actually I'll be introducing today here started from such research collaboration. So yeah, like being able to present this result with you and also in front of Professor Shin means a lot to me. So thank you again for hosting me here today. So I will be talking about data-driven safety frameworks for safety verification with a specific focus on its application to advanced air mobility today. As a person who studies controls and robotics, my lifelong vision is to develop autonomous machines that helps human society. And of course, there are like so many various research challenges we have to solve together to achieve this vision. But one of the most crucial kind of challenges I strongly resonate with is how do we guarantee the safety of such autonomous machines? So these days, as we see autonomous machines deployed in the societal scale level, such as the self-driving cars or in the unmanned air vehicles, but we see that like even a slight possibility of safety violation can lead to catastrophic results, as we have seen in this industry, such as the Cruise incident or the Boeing 737 MAX incident. Not only that, the violating safety is detrimental for the human society, but also apparently safety guarantee has to become the crucial foundation for the sustainable and the reliable operations of these autonomous machines. And we'll look into why guaranteeing safety for such autonomous machines is really difficult for these systems, especially at the societal scale level today. And I'll describe that under this specific context of the application in advanced air mobility systems. So this advanced air mobility system, like AAM, is basically kind of the next generation air mobility system, mainly driven by the innovations in the unmanned air vehicle design. And there are various decision-making layers, starting from the operational level all the way down to the vehicle and dynamics level. And the safety challenges exist in individual layer and also at the system level that encompasses all these layers. So at the vehicle dynamics level, the main challenge for this new generation aircraft vehicle is that their dynamics are highly uncertain. So especially the so-called electrical, like vertical takeoff and landing vehicles go through the flight mode transition, usually from the hover mode, which is used in the takeoff and landing, and all the way to like the cruise mode for the efficient, operation and flight. But during this flight mode transition is when these vehicles are extremely kind of vulnerable to the loss of control, which can lead to catastrophic failures. Because these aerodynamics between these vehicles are hard to model, and then they're really vulnerable to stall conditions. So how do we guarantee safety despite such uncertainty in the dynamics is one of the crucial challenges these vehicles might face in the future. Yeah, and during the flight tests, or also in the flight, during the actual operation of these vehicles, these kind of accidents due to loss of control has actually happened before. More kind of specifically, the research question I'm asking here is how do we extend this control-theoretic safety guarantee? So when we think about safety guarantee, we usually look into the control literature, because in the control literature, people can use models of the system to provide such guarantee. But how can we extend such assurance principle in control theory to the setting where there are like a lot of uncertainty in the systems, which is hard to model, is one of the crucial challenges I want to address in my research. And to address this problem, I want to extend this assurance principle in control theory by combining with data-driven approaches and machine learning-based approaches. So this will be one of the central themes of today's talk. So in the first technical component of the talk, I'll briefly introduce how we can construct a safe operation region directly from trajectory data that are conducted also safely in the experiments without using any explicit model information. And then at the at the routing operation or like the path planning level, there are also many challenges, especially as we see an increasing volume of these aerial vehicles in the sky. There is a growing concern that the manual air traffic control cannot handle such rising volume of the traffic. This kind of incidence is already happening, as we have seen earlier this year in the tragic mid-air collision accident in Washington, D.C., where this incidence was happened because of the air traffic control not being able to handle this situation. So there is a growing need in this air traffic control community to automate this traffic control. And many promising approaches are being developed, such as the multi-engine reinforcement learning. But of course, without appropriate safety measure, deploying these learning-enabled algorithms pose significant risks for failures. So in the second technical portion of the talk today, I'll be showing how we can devise a better safety measure to make these learning-enabled systems more safe and also more efficient. So together, these two technical portions will constitute the main part of the talk, and then I'll wrap up my talk by briefly discussing the key challenges and opportunities for this advanced air mobility. Before that, I would like to jump into a brief background and motivation for this talk, for the technical part. So because I'm going to talk about safe decision making, we have to talk a little bit about control theory. I'm not sure how many of you here are working on control theory, but I'll try to make it as easy as possible. If anyone has questions, feel free to interrupt me anytime. So when you think about safety problem, we want to divide these problems into two fundamental problems. So consider this, sketch of the safety problem where the vehicle is trying to fly near this building, and the safety constraints is given to the vehicle, like basically avoid the collision with this building. And why is this problem really hard? Is because even when this safety specification is already given, which is like the constraints are already given to this problem, within this constraint set, not all state is safe for this vehicle. So basically, there are some states within our constraint where no matter what the vehicle do with its control, in the future, it will be inevitably falling into this failure region. So the first essence of this safety problem is verifying where those failure regions are in our constraint region and excluding them and figuring out what are the dynamically feasible safe sets within our constraint region. And this is actually a pretty challenging problem because, as you can see, we have to figure out the vehicle dynamics. We have to combine the information with our constraints and then, basically carve out all the regions that are unsafe. Once we are able to find such safe set, the second problem is basically making sure that the vehicle only executes the safe action that maintains the vehicle within these dynamically feasible safe sets. So basically, if the vehicle, here let's say the vehicle is trying to do something unsafe, then we will make sure that we filter it so that we only apply the safe actions during the deployment. So designing such safety filtering mechanism or safe control, finding such safe control in general is the second fundamental problem for this safety. So in control theory, there's a very useful concept called certificate functions, which combines the two information, the safety constraint and the long-term effect of the dynamics, into a single scalar function, which is useful to solve both problems. So it looks like this scalar function, energy-like scalar function. And usually, once we are able to construct such certificate functions, its level provides the information of the safe set within our constraint region, or also like distance to our failure region, kind of like a safety margin. And also, its gradient can be used to evaluate what are the safe control direction. So how do we compute or verify such circuit functions? Because if we can verify such circuit functions, we are able to solve this problem. And in model-based control theory, basically, there is a technique called the Hamilton-Jacobi reachability framework that solves this problem by formulating an optimal control problem. So here comes the math. So we will consider this vehicle as these dynamical systems described by this ODE, F, and then we have this various control signal we can apply to the vehicle so that we can control the vehicle. And we want to make sure that the vehicle stays within that box region, our constraints. And again, so depending on the control signal, it can stay safe or it can go out. And what we want to do is rule out such states where no matter what we do with our control, the vehicle will eventually fall out to the failure region. So if you effectively rule out all such vehicle conditions, then we can solve for our maximal safe set. So this is the high-level concept. And we will formulate this as an optimal control problem by considering this cost function. So basically, it is like a distance to our failure boundary. And then if the vehicle tries to maximize such distance, and such distance can become non-negative or like positive, then we can maintain the safety. So we formulate this optimal control problem where the control, you can see, is trying to maximize such a cost function. And then we can solve this value function because this is an optimal control problem. Similarly to reinforcement learning, we applied dynamic programming to solve this problem. The only difference from the RL is that we do this in the continuous time formulation, which results in such like the so-called Hamilton-Jacobi partial differential equation. Or maybe before that, one thing I should mention is that once we are able to verify this value function or to compute this value function, the safe set will become the super zero level set of the value function. So all we have to do is compute this value function. And to compute this value function, if we derive this dynamic program principle underlying this optimal control problem, we have this Hamilton-Jacobi PDE. So all we have to do again is just to solve this PDE. But here is the challenge, especially for the uncertain dynamical system. Within this, the term called H, the Hamiltonian looks like this, where we use our information of the dynamics. So this is where the dynamics come into the play to verify circuit function. And through this Hamiltonian, we are blending the information of our constraints and the dynamics to compute such circuit function. And the main challenge is that going back to the previous motivation part, for systems where the dynamics are uncertain, this problem is intractable. So the motivation question here is, can we do such reachability analysis only using the data without any model of the system? I briefly went through this, but I'll go back to the practical motivation one more time. So this new generation vertical takeoff and landing vehicle, I have collaborated with NASA on verifying safety safe sets using the reachability for this tilting vehicle, and I also interned at Joby trying to provide safe operation algorithms for this vehicle that goes through the flight mode transition. As you saw before, this vehicle accidents due to the loss of controls have actually happened in the past. And now from taking this control perspective, the main challenge is that this F changes during the flight mode transition. And also it can be affected by the operation conditions of the vehicle, like the airspeed or the airspeed or the weather, things like that. And since this vehicle have varying configuration, it's really hard to model individual underlying aerodynamics. It's really computationally expensive. And even when they do so, they usually lack the closed form mathematical model. So you cannot write down the equations for F and then solve this Hamiltonian. And finally, even worse, even let's say you have some approximate model, usually this approximate model, due to the nonlinear aerodynamics term of the vehicle, they don't have a good structure to solve this optimization problem efficiently. The only silver lining is that when these vehicles are tested, extensive data are collected. So the main motivating question again is, how can you leverage this data to provide the safety or verify the safe sets of this vehicle? So we've worked on this problem with Namun Cho, who worked with Professor Shin at Cranfield University, and he recently joined Seoul National University. And one of my lab mates, Christopher Strong in Berkeley, a framework that can solve this problem. So going back to solving this Hamiltonian, we will first try to translate the problem a little bit into a more tractable form. So instead of thinking about that small f, which is hard, which is uncertain, we'll translate into the velocity. It's just like a substitution where v indicates the velocity of the state. And then now we will consider all the possible velocity bound given an appropriate like control. So if you take control, like a particular control, the state will have a particular velocity, and then we'll think about all the possible velocity. And by taking this perspective, we can view the problem in a very geometric way. Then the nice benefit of viewing the problem first in a geometric way and also taking this substitution is now that our objective function, at least in our objective function, we have a linear objective function, so it makes it a little bit easier. But then we still have the problem that our f is unknown. Our large f, which is all the possible velocity, is still unknown to us. Well, now with this representation, we can kind of take a more geometric perspective. So then, when you think about how all these possible velocity bounds vary in the state space, the vertical axis represents the state space and the horizontal plane represents our velocity. You can see that, depending on where the vehicle is, we have various possible velocity. If you take the, top-down view of this problem, we have such unknown, velocity bound. And then if we want to find a given p, a particular direction that maximizes this objective function. So we want to find this point. And then still we don't know this underlying velocity bound. But now we have the trajectory data. And then from this trajectory data spread out across the state space, we can project them into the current state we are interested in. And then at the current state, we can think about what are the possible realization of the velocity we can infer from our trajectory data. So if we do this, we can formulate this so-called data-driven Hamiltonian, where we always consider the worst-case realization of such uncertainty we can infer from our trajectory data, and then we take the best guess among the data. So there are like a lot of kind of dirty math behind this formulation. But actually the nice thing is that it doesn't depend on any specific like modeling. So it doesn't require us to model f, the small f, our dynamics. And also this is a convex optimization. It is like a very special case of the linear optimization that has a closed form solution. So it is really computationally kind of efficient to solve this problem. All you need is like a batch of trajectory data to have a good approximation. And then an important, like a crucial theoretical guarantee of this formulation is that the resulting data-driven Hamiltonian is guaranteed to be the under-approximation of the ground truth Hamiltonian. And why is this important? Is because if this is a guaranteed under-approximation, if you plug that into our Hamilton-Jacobi partial differential equation, which we solve, then we get this value function, v hat. So v hat now is this data-driven safety value function. Then this value function is guaranteed to be the under-approximation of the ground truth value function. As such, since the zero super level set of this value function provides us the safe set, we have a guarantee that our safe set is an inner approximation. So we always have a guarantee that we estimate our safe set conservatively, which is crucial. So now we'll look into the numerical example of how we can implement this for this actual like flight vehicle. So this is a pretty old vertical takeoff and landing model like developed in the 70s and 80s. But this is almost the only model, only vehicle out there where someone has published a specific aerodynamics table of this vehicle so that we can kind of construct like a ground truth model of this system so that we can kind of compare to our results to the ground truth results. So we can describe the system's longitudinal dynamics in this redisordered state. The V indicates the speed, airspeed of the vehicle, and then the gamma indicates the flight path angle of the vehicle. And then this dynamics looks rather simple, but actually the L term and D term here are the lift and the drag term. So where a lot of the hidden nonlinearity is, and this lift and drag term also has a lot of uncertainty. So this is why solving this problem is still challenging. Since we roughly kind of we assume that we know such aerodynamics table for at least for this particular vehicle, we can approximately solve for the ground truth kind of safe set of this vehicle and then compare our data-driven results to this ground truth result. And then how we can collect data actually for this vehicle is that we start from a very conservative safe set. It's a pretty conservative safe set that with like the most first principle analysis the designer can solve. It is kind of assumption that flight test will never be executed without knowing that at least the vehicle can hover. This is like this conservative safe set can be considered as a very, very conservative kind of like set point that the vehicle can operate. Starting from such a conservative safe set, we will execute experiments within the previously estimated safe set, and then we will add those data, and then we will re-evaluate our data-driven Hamiltonian and recompute our value function. So then by computing this value function again, we can update our safe set. Basically, we can expand our safe set. And then once we have expanded our safe set, we can conduct more experiments in new region. Then we can iteratively collect more and more data by taking this iterative approach and conduct all of the experiments safely. So in this three-dimensional state, the beta is the tilt angle of the vehicle. Again, the v is the speed of the vehicle, and the gamma is the flight path angle. So this yellow like kind of tube is the first most conservative operation region of the vehicle that smoothly transitions from the hover mode to the cruise mode. And then we start our experiments from this conservative region. And in each iteration, we roll out 20 initial states and then conduct the experiment. As the vehicle approaches the safety boundary, we kick in our safe control we derive from the data-driven Hamiltonian and prevent the experiments from exceeding the previously verified safe set. And then once we do that, we add those data into the new data set, and then we recompute and expand our safe set, data-driven safe set. So that procedure, I think we do like 20 iteration, looks roughly like that. You can imagine this like the flight test team of the air taxi company. Each day they execute 20 like trajectories or 20 experiments. They add them to the data set. They sleep while waiting for the safe set to update. They come back the next day, they see the safe set expanded, then they do a new experiment. But this is actually like what people do in the flight test community. Like they gradually expand this flight operation region, but with a less kind of principle, like with much more heuristics and much more, much more heuristics. Yeah. So we are basically providing a control-theoretic framework to do that more efficiently. And then, like, for example, if you look into the iteration 4 closely, some of the experiments are conducted near the hover condition, some of them are conducted near the mid-transition condition, and some of them are conducted in the cruise condition. And each data points or each trajectory provides us new information so that we can use those information to reason about what are the actual safe sets. And then once we've ended this iteration, we can basically do it more and more. But once we have ended at with 20 iteration, the volume we recovered from the data-driven safe set is actually 50% of approximately 50% of the ground truth safe set, which is not terrible. And as I showed you before, this theoretical guarantee that this data-driven safe set is an under-approximation of the ground truth safe set can be, you can see that that's actually true in this visualization. So to summarize this first part, our data-driven Hamiltonian, we hope that it provides a new paradigm for integrating the model-based analysis and the data-driven approaches for safety without explicit modeling of the underlying dynamics. And then the key idea we could circumvent such explicit modeling was by taking this effective abstraction that represents the dynamics with the velocity, not with the like ODE. And we have a guarantee that that our verified safe set is always the inner approximation of the ground truth safe set. So just before moving on to the next part, we are actually extending this to various ways. The current work was limited by the assumption that the data is given, like the clean data is given to us. But in real experiments, that you have like all sorts of errors, measurement errors. So we have extended this to the case where we have measurement error and then also disturbances in our trajectory data. And then we're also extending this to the setting where we are not only solving the reachability problem, the safety problem, but we're also solving a more general optimal control problem. So we hope to publish that result sometime soon, next year. Before I move on to the second technical part, are there any questions? Yeah?
How did you calculate the ground truth value function?
The ground truth value function is like ground truth, but we discretize our control option, and then we evaluate the Hamiltonian under such control, and then we take the maximum. So it's also still like a kind of like a numerical approximation of the ground truth. Yeah, but it's computationally expensive.
It seems it's quite data dependent.
Yeah, it is.
And you have to, first you have to get the data, and then figure out the subset, and then you spend a little bit more, and then get the, again, subset,
Yep.
and then explore these. Do you have any way you can best explore the data, so you can effectively figure
Yeah.
out the network subset?
Yeah. So that's like a really, really good question. And I think one of the key underlying research problems here is like what are the good exploration strategies? And also, under such exploration strategy, what is like a sampling complexity? So let's say like we want to achieve like we want to verify the maximal safe set, the ground truth safe set, like like how many samples we actually need to get there. I think those are a really important question. It really depends on what kind of exploration strategy we deploy in our experiments. In our paper, we deployed something quite heuristics, like I think we did something like, since we need to expand the safe set in various flight path angle, like let's just ask it to like increase or like decrease the flight path angle, something like that. So we deployed a little bit of like heuristic kind of to do these experiments, but there should be a lot more like theoretically grounded approaches to solve this problem.
Can you find the theoretical bound of the Hamiltonian approximation you have?
We in the follow-up paper, we have proved that asymptotically, if we add more data, the data-driven Hamiltonian converges to the ground truth Hamiltonian. So that's kind of your question. Yeah.
So also P, your P, I figure out, in my opinion, after you're solving PD, you get the P.
P actually can be any value, but when we solve the PD, P is a gradient direction. So P is actually the gradient of V. So every numerical step, we have different P at every different state. Yeah. P is like called a co-state.
So you, depending on the XL approximation of the value function, you get the gradient and then use this P.
Yeah. To execute like a safe control. So we can evaluate like an approximate safe control from our data-driven Hamiltonian. That's what we do when we do experiments. These safety filtered ones are using such gradient of value function. Yeah. Okay. Yeah. So let's move on to the next part. Like the first part was a little bit control theoretical, like maybe too much for people who are not in the control theory community. So I'll move on to the next part, which is a little bit more relevant. I guess my guess is more relevant to the Graduate School of Mobility. So here we were trying to combine this control theoretic safety tool with multi-agent reinforcement learning. And again, the main motivation is that like air traffic community definitely have a lot of layers to provide, like 10 to the minus 9 safety guarantee. Starting from the airspace separation, centralized manual air traffic control, protocols to make sure that if the two vehicles actually engage in the air, they follow this protocol so that they avoid the collision. And then like more recently, they have developed these kind of autonomous collision avoidance modules deployed in these conventional airliners. But the main problem we foresee in the future is when this traffic volume really increases in this advanced air mobility era, such layer, like there will be many failures across this layer, such as this centralized air traffic control will actually be replaced with decentralized air traffic operation based on the announcement of FAA. And then because they are decentralized, the operators might have conflicting objectives when they execute their traffic control. And also these protocols are mostly designed so that if the two vehicles engage, they can avoid collision. But what if in the same airspace there's a third vehicle or like fourth vehicle? So those are the kind of reasons why in this really high volume air traffic scenario, this conventional paradigm can fail. And then this has happened quite more often than you expect. The mid-air collisions due to the failure of such modules. So the main motivation for this project is, can we devise decentralized autonomy stack deployed at the last layer for this vehicle for safety? Now going back to control theory a little bit. So by solving, as I showed you before, by solving this reachability safe set, we can solve for the maximal safe set. So in this toy scenario, we have 3 vehicles, and then each vehicle is facing in various direction. And then if we evaluate the pairwise dynamics, so from the yellow vehicle perspective, which is our agent, we evaluate the relative dynamics to the cyan one, and then also we evaluate the relative dynamics to the blue one, and then we can compute the safe set with respect to each vehicle. So that is the boundary I'm showing you from our reachability computation. So what I'm showing you is that if this vehicle is outside that boundary, like for example the blue one above, it can avoid collision to that vehicle. Same for the cyan. So in this specific case, do you think that the yellow vehicle is safe? According to the theory, it sounds like it, but like many people actually, when I ask these questions in my talks, they say, oh, they don't look safe. Like they'll probably collide with each other, and that's kind of true. Like this, when we execute like kind of the optimal control we get from reachability, they still fall into this near collision. Like the distance between the vehicle go below our minimum separation distance. And why does this happen? Is actually a known issue in reachability called the leaky corners. The leaky corners basically mean that within the intersection of the two safe sets, there are regions where satisfying both constraints at the same time is impossible. So there's this gap between individual safe sets intersection and the safe set that wants to satisfy both constraints at the same time. So why the vehicle is unsafe in this particular example is because the vehicle is inside the leaky corner. And verifying the leaky corner is a non-trivial problem, because now if you want to brute forcefully solve this problem, you have to consider the relative dynamics of all 3 vehicles, which increases the dimensionality of the problem. And then if even yet lets you do that, let's say you can do that, you have another vehicle coming, then you have to solve another problem. So this can continue more and more, especially in this multi-agent context. And I kind of, from the control theory perspective, again, I pose this problem as one of the most fundamental challenge for safety in the multi-agent context. So in our work, we try to solve this a little bit by combining with multi-agent RL approach. But before that, we first defined this region, which is what we call the potential conflict region. Within this potential conflict region, the leaky corner issue can arise if there are more than 3 agents. So one agent can enter this region. One agent entering is fine. They can actively engage each other to avoid collision. But now, if there's a third agent that enters this potential conflict zone, then there's a possibility that this leaky corner issue can arise. So kind of the high-level idea we deployed is that maybe we can allow one agent to enter, but then we can incentivize the learning algorithm to penalize the third agent from entering this region. So it's like posing this potential conflict zone as another soft safety constraint to the vehicle. And one of the main reasons actually we pose this not as a hard constraint, but as a soft constraint is because if this becomes the hard constraint, then there's like the next layer of leaky corner of this hard constraint. So it's like this can pile up and more. So that's kind of the reason why we consider this as a soft constraint. And it's also that even if the vehicle enters this potential conflict zone, there is a possibility that it can deconflict by avoiding the leaky corner. So we only impose this as a soft constraint. Another important thing is that this conflict zone radius can be computed by taking the reachability analysis. I'll not go into the detail of that, but in the paper we compute the distance based on the reachability analysis. So this is not a heuristic design. This potential conflict zone radius is determined by the dynamics of the vehicle and by doing the reachability analysis. So yeah, as I said, when we train our multi-agent reinforcement learning algorithm, we actually, if the vehicle sees that there could be a potential conflict zone in its navigation path, it'll try to avoid such potential conflict zone. That's how we incentivize our multi-agent RL policy while they try to achieve their, to get to their waypoints. And then once we do that, after that is the more rigorous safety layer. So basically within the kind of perception limit of the individual vehicle, they evaluate the collision risk, basically the reachability value. As I said, reachability value becomes the safety margin. So we evaluate this safety value against each individual agent, and then we take the lowest one, and then we do the safety filtering using our reachability technique or our safety control technique. So by taking this layered approach, at the first layer, they try to avoid potential conflict zone, and then the bottom layer, they do active deconfliction to avoid collision. And we have shown that this can achieve a much higher safety rate and also a much more efficient navigation. So, yeah, as I said, based on the vehicle dynamics, we can evaluate the safe set of the vehicle, and then based on the safe set of the vehicle, computed safe set, we can also evaluate the conflict zone radius. We have done this for the quadrotor and the air taxi vehicle. The quadrotor, the main feature is that they can hold their position in the sky, which makes kind of the safety mechanism a little bit easier. But for air taxi vehicle, they have this minimum velocity for prevent the stall. So their deconfliction is much more complicated than the quadrotor. So for quadrotor, we have done this in the lab setting, the experiments. So here, there are 3 vehicles here. And then there's this virtual waypoint in the air that the vehicle has to go through to get to their goal point. And if, notice the behavior of the yellow agent. And if this multi-agent RL is blind about potential conflict issue, then you can see that the yellow agent is actually blocked by this other 2 agents because of the safety filtering, so that it misses the first waypoint, and then it has to go all the way back to go through the waypoint. So that makes the navigation really inefficient. And if you deploy our safety-informed RL policy, you can see that the yellow agent waits until the first 2 agents go through the waypoints because it is aware that if it enters directly, it can induce this potential conflict zone issue. So that makes this behavior emerge, and then the vehicle can, all the vehicle can achieve to their, reach their goal much more efficiently. We have deployed this in the simulation of the Bay Area. So this is various takeoff locations in the Bay Area. One of them is my school, Berkeley. And then we have this hypothetical scenario where all agents are trying to merge to get to San Francisco. So this is a hypothetical air taxi scenario. In the morning, people are trying to now commute to the downtown city by taking this air taxi, and all air taxis trying to merge to this corridor. And then, as you can see, if the multi-agent RL policy is safety blind or is non-aware of the potential conflict zone issue, the safety filtering, we still apply the safety filtering, the reachability-based safety filtering. You can see that in many cases, this active safety filtering can mess up the operation pretty bad. Like the efficiency of this operation is pretty bad. And it also even sometimes have like these near collision instances. By deploying our approach, we can see that the entire operation becomes much more efficient. You can see that the deconfliction kind of maneuver is much more efficient, much more natural. It's closer to what the pilot would do. And like the travel time has decreased significantly, and we still sometimes have a little bit of near collision, but it has reduced significantly as well. I just want to mention that like having like really zero is not possible, mainly because, again, of this leaky corner issue in this multi-agent scenario. Okay, so to summarize our work here, we pose these conflicting safety constraints as the main issue for the multi-agent safety. And we devised this layered multi-agent algorithm that takes into account the potential conflict region as the soft constraint. Any questions before I move on to the final part of the talk?
So when you build safety set, did you assume other agents are not maneuvering but with a constant velocity, or did you also incorporate the cooperation of the other agents when you try to figure out the safety?
So the safe sets are computed based on the relative dynamics between one agent, the ego agent, and one other agent. So both the dynamics of both agents are considered. Yeah.
So the other agents also can maneuver.
Yeah. We are considering that. Yeah.
So they do calculate also the safety set and try to.
Oh yeah. So one kind of assumption we have is at least for safety, they coordinate with each other. So my safety filter exploiting this vehicle and the safety filter exploiting the other vehicle are synced, but they're not synced in the explicit way. They just evaluate the same relative state, and then they execute their own individual safety filter. It's just that the safety filter designs are identical, so that if they both execute the safety filter, then the safety is guaranteed. Yeah. So there's no like explicit communication or anything, or like they're not centralized, but assuming that they will deploy the same safety filter, they have safety guarantee. Yeah.
So it's kind of like bound rather than the actual safety set.
It's kind of like what?
Bound. It's rather because you might have different kind of like safety feature implemented. But you assume that they.
Oh yeah. So here another assumption we have is they all follow the same safety protocol, although they're like decentralized. We haven't considered a scenario yet where there's like a adversarial agent or like a third-party agent that has a totally new safety protocol. But that, if such vehicle appear, we can still use such technique, but we have to assume that, we have to assume the worst case instance. So we have to assume that this other vehicle might do the worst case kind of action. Yeah. Okay. So then I'll try to wrap up my talk by just throwing some thoughts I have these days about this advanced air mobility. So I think one of the key challenge of this high density advanced air mobility is these interactions between multiple layer. So in the conventional paradigm, this conventional way people have been solving this problem for conventional aviation, they have implicit assumptions that each of these layers have sufficient time scale and spatial scale separation so that individual layer in most cases doesn't interfere with each other. Like the decisions at the operation level doesn't affect kind of the decisions at the vehicle dynamics level. They just pass their reference information to the vehicle, and then does the vehicle follow it. But I think as the traffic volume increases, and also there are like a various more uncertainty appearing the problem because, like, for example, the air taxi service will be something like Uber on demand. Such uncertainty coming from the operation level, or also uncertainty stemming from the vehicle dynamics level, will start to engage each other and affecting the decisions at the other layer. So I kind of, expect that this will cause more issue in the future when we actually see these high density air mobility operations. Like regarding safety problem, then we also have to think about what are the main safety risks we have to kind of account for when we make decisions. So like, do you want to think about safety risks at the ground operation? Like, for example, each vertiport or like this helipad might have limit of how like safely they can operate. Also, like they have to consider this uncertain user demand or charging schedule. So do you want to consider all the safety risks at the ground operation level? But you probably want to also consider safety risks due to uncertain weather conditions. You want to consider, You want to consider safety risks due to high density traffic volume, like the congestions in the sky. Let's say in the lower layer, like safety risks because such deconfliction instances happens. Also finally like safety risks at the individual vehicles, like one of the propellers of this vehicle went off, or like their battery is about to die, things like that. So as you can see, like if we actually see the air taxi services in the future, all of this poses kind of quite significant safety risks to the designers of these decision-making systems. And my main kind of philosophy here is that we need to start thinking about problems start to think about questions that can provide us better system-level analysis, verification, and design tools. So systems level here means we should not too much focus on separate layers. Maybe because these separate layers will affect each other in the future, safety risks at one layer will affect the other layer's safety. So I think we need to think about how we can provide better framework that provides us this system level safety guarantee, not only in terms of safety, but also in terms of better operation, more efficient operations and whatnot. So I consider this as one of the main challenge for the next generation air mobility. And then, but the opportunity here is that these new generation companies, but also even like including the conventional companies, they have a lot of data, like airliners, like companies like Boeing, like conventional aircraft companies, or also like new generation company like Joby or Archer. They all have vast amount of data they collect from the actual operations or also during their flight tests. So my hope is that we can leverage this data to provide better schemes or like better framework for more efficient and safe operations of this vehicle. And the final challenge is, if we are going to leverage data and learning, how do we, again, guarantee safety? And I think this is still like a quite open question. Like I have shown you some of the work I've done, but that definitely doesn't solve every problem. And if we don't provide rigorous guarantees or like provable guarantees for these systems, we might see in the future again instances like this happening again that can risk people's lives. So with these challenges and opportunities, I would like to end my talk. Maybe before that. So I think AI work works techniques in AI and techniques in control theory can be combined to achieve this goal. Yeah. So and then with that, I would like to end my talk. Thank you so much.
Any question? Soyan, no question?
Actually, I have a question.
Yeah.
How did you estimate the transmission dynamics? The aircraft have the different dynamics there in the
Yeah. So here we are assuming that dynamics are given. So it's separate from the first part. So we are assuming that the higher level dynamics, like the path planning level of dynamics, is kind of given to the vehicle. And there might be some uncertainty of such dynamics. We can consider that by computing like a robust valve function that incorporates some kind of error. But for the second body of work, we are kind of using explicit model of the system. Yeah.
Any other questions? People are avoiding my eyes. So it's a great talk. Thank you for a very nice talk. As you mentioned, maybe we start to consider the entire system as a holistic view.
As a what?
As a holistic view.
Oh, yeah.
You mentioned 3 layers. Typical approach we had was we separate the
Exactly.
layers, under the assumption, as you mentioned, separation principle, and also the abstraction theory and biosimulation theories, and so on.
Yep.
So we assume that, yes, once we have this one, we can realize the other on the lower level and so on. And first, once actually you have like a high volume of traffic, you might start to have like a fast trajectory, like training and so on. Then it's interfere with the low level system dynamics and so on. Therefore, you can't separate anymore. Also, if you start to have some faults in the system,
Exactly. Yeah. Yep.
then it becomes like impossible to take this approach. But the question is, how can we actually
Solve this.
explore any potential approaches you are thinking?
So yeah, I believe that we should take modular approach. Like so, basically, like how do we provide a framework that is computational tractable is probably important. One thing we know is that higher level decisions can be done in a slower rate, so they can be a little bit more like computationally intensive. I think there wouldn't be like a kind of single algorithm or like a single program that solves all of this altogether. Like there will be modules still at each layer that will be communicating with the other layer and then solve their own decisions at their own rate. So, but still they have to be aware with what's happening at the other layer, and then that's kind of the one thing I don't see a lot in the literature. Like these, let's say in the routing level, they're not very aware of what individual vehicles like are kind of facing at the moment. So my kind of proposition here is that we need to think about, like even when, let's say we deploy we try to deploy the conventional routing algorithm, they have to, consider what's happening at the bottom layer. So yeah, like at each layer, there should be a way to make their, calculate their decisions computationally tractably, but then they should still consider the situations at these other layers. That's kind of what I'm trying to say here.
Yeah. You can think, I think, potentially 2 potential approaches in my opinion.
Yeah.
One is like just end-to-end. I don't know.
Yeah, but the end-to-end, like if let's say we use like VLMs, maybe this can be solved. Yeah.
But thinking about the size of the problem, this might not be the wise to option. The second approach is, as you mentioned, is just a modular approach.
Yeah.
But we use conventional modular approach, which we say this may be not sufficient enough to handle the safety issues we will encounter in the future. Right?
Yep.
So I was thinking we have modules, and the connection of the modules typically is handled in very classical way still. But we can also handle these connections between the modules in like a more AI-driven.
Yeah, exactly.
And then try to have the safety guarantee on this connection on top of the individual safety guarantee. But becomes, I don't know, a bit like overlapping and so on.
Yeah.
2 ways that we can handle. The question is, in this case, we need to believe handle safety one by one, because we design modular parts and we try to get the safety. But even if we do this, we know we combine these two, even if they have
Individually can work. Maybe after we combine them, they can fail. Yeah, which is quite possible if you know control theory. So I think there are tools in formal verification literature, like for example, assume guarantee contract. I think that can be quite promising to be used to evaluate whether the connections between the layer or like modules actually, or like the entire system integrating these different modules, like whether they can be safe or not. Like these formal verification tools are developed to do such thing, but like they usually operate by kind of abstracting what individual models are capable of, like, oh, what are the assumptions, and what are the guarantees they can make, and then they just stitch together and then see if, like, what are the system level, guarantee we can have. Yeah. So I think those kind of modular approach are what I'm trying to refer to here. Like that looks promising. Yeah.
Well, as you mentioned, formal methods still can assume that this is safe and this is safe. What if this is the case, and then so therefore this is more like some logical flows guaranteeing the safety. What I was thinking was like where I'm heading, trying to head to is like a leaking condition which is shown. So we have different layers, and then the safety of this one can be guaranteed, but when combined,
Yeah.
as you showed, we can have failure.
Yeah. Exactly. Yeah.
So maybe we can take a very similar approach just to show it.
Yeah.
To have this different layer approach, modular approach.
Yeah. And actually, there are some work that are doing that. Like basically, they think about all these various modular like reachable sets, and then they combine them, and then they see if there's like any leaky corner or not. Then if they see leaky corners, they reevaluate the like combined safe set. So yeah, I do believe that like techniques like this can also be useful to handle those problems. Yeah.
Great, thank you.
Yeah. Thank you.
Any other questions? One last chance. No? Great. Then please join me.
Yeah. Thank you so much for everyone.
Speaker.